On one hand, we want to become more conversant with different ways of using notation to depict a set. And on the other hand, we want to get comfortable using operations, and specifically the operations of union, intersection, and complement, to create new sets out of old, and relating those operations to the kinds of logic that we already know about from earlier chapters. So the most important first thing we need to be able to do with sets is to be able to describe them, be able to communicate with one another to say exactly what set of elements am I trying to talk about. And there's really sort of three different ways in which mathematicians use notation to talk about sets. I would say the first and the most primitive, this is sort of a satisfying at a gut level, is what's called the roster method. When I say the roster method for describing a set, what I mean is an attempt to physically just list out all of the elements that are in my set. So for example, if I list a set whose roster consists of the elements that are the numbers 1, 3, 5, 7, ... Probably most acculturated mathematicians / students of mathematics / anybody who's had a course in which you've talked about what even and odd numbers are, I think most people would understand that what we mean when we write out those first four numbers and then ... is we're probably talking about the set of all positive odd numbers, right? And so that's a second very important way to communicate about what set we might be talking about, is just to say it in words. A lot of math students will shy away from using verbal language and vernacular. Please don't. It is the way that we communicate with one another. We don't always use notation all the time. You're not going to find notation on the pages of the New York Times, even when the New York Times is talking about a mathematical idea, right? We use words like I'm using words right now. So never be hesitant to just write down using words in your whatever language, native language that you use to communicate mathematics. Words are a very powerful way to communicate. And so that verbal method of communication is going to be method number 2. Probably the one that gets the most, the one that keeps people up at night the most, is the third way of communicating. And it's also kind of the most precise and most powerful, and it's also the most daunting and confusing the first time that you look at it. And it's called set builder notation. And in set builder notation, we describe the elements of a set using sort of two criteria. One of them is it tells me what form those elements take, and that's a piece that comes before either a colon, which is what we're going to use here. Sometimes it's a vertical bar that's placed in the notation to divide what's on the left, which is sort of like almost like a domain. It's kind of where are my elements of my set coming from and what do they look like. And then on the right-hand side, some sort of a description, which is usually some combination of logic, vernacular writing, and notation. Maybe there's some equations, maybe there's some inequalities, but basically on the right-hand side of this colon, we say what are the criteria for membership in this set. So it's like, what kinds of elements do we have, and then what criteria do they have to satisfy in order to belong to my set? So for example, if I'm thinking about the set of all odd positive integers, which has the roster 1, 3, 5, 7, ... what I could say, I'm going to think about the criteria for membership. Just by the definition of odd number, we know that the odd numbers, for example, can be written as twice an integer minus 1. Right? For some integer, which now we're going to specify here that the integers are part of the natural numbers, so that what we get are the set of all odd positive integers. So we say that the criteria for membership in my set, all of the x's that belong to my set have the form 2y minus 1 for some natural number y. And so in the set builder notation, we put curly braces around the whole thing to denote we're talking about a set. We write the criteria for membership in my set on the right-hand side of the colon, and then the form that the elements take on the left-hand side of the colon. Sometimes on this left-hand side of the colon, we'll also be real specific about what universal set these elements might be coming from. So as an example, in this question number 1 here, we see some set builder notation where we're saying x is equal to 3 times k for some integer k, right? And we're also sort of confirming on the left-hand side here that those elements x that belong to my set are also going to be taken from the set of integers. So very often we'll use the universal set as another thing we put on the left-hand side of this notation to just kind of tell where these things are coming from. And again, the way that you sort of silently read to yourself a mathematical sentence, I think has a powerful lever in making sure that you understand what it is that you're reading. And so when I read set builder notation like this thing in number 1, the way that I would read this is that I'm reading the set of all x's which belong to the set of integers, which another way to say that is that's the set of all integers x, such that x is equal to 3 times k for some integer k, right? And sometimes the best way to decode set builder notation is just to do that exercise, read it in your head, and then just translate it into written words. So if I just wrote down that sentence that I just said, it's the set of all integers x such that x is equal to 3 times k for some integer k. That is a good first step to getting meaning out of set builder notation so that you can understand and convert it to different forms of expression. So the one I want to quickly touch on is the middle row here, which is given to you as a roster. And as a roster, it consisted of the numbers -8, -7, -6, up to +10. Right? And so one of your groups listed that in writing as the set of all integers that are greater than -9 and less than 11. But then there was another group that listed that as the set of all integers from -8 to 10. So let me real quickly ask the question, is there any difference between the ways that you've described those two? So on the one hand, this was group 2, said it was the set of all integers from -8 to 10. Group 1 said it's a set of integers greater than -9 and less than 11. Are those both talking about the same set or not? One group has decided to use what we call strict inequalities, greater than and less than, to describe the set, right? The set of x's such that x is an integer, it's greater than -9 and it's less than 11. And the other group has chosen to use what I sometimes call permissive inequalities, non-strict inequalities, less than or equal to, right? It's the set of all integers which are greater than or equal to -8, so that explicitly includes -8 as well as everything greater than it, and also less than or equal to 10. Right? So it includes 10, it also includes the things that are less than it, right? And those inequalities have carried over into their set builder notations for these sets, right? So both groups have said this is a set of all integers x, so the set of all x's that belong to the set of integers, such that either -9 is less than x is less than 11, in the case of the strict inequalities, or -8 is less than or equal to x is less than or equal to 10 for the non-strict inequalities. So that's a good example of how the same roster can give rise to different descriptions of the set, both verbally and then also correspondingly in the set building notation. But any of those answers, again, is describing the same set. We can see that by trying to list out a roster and noticing that it consists of the same elements. And two sets are equal precisely when they consist of all of exactly the same elements as one another. Any element in one of them is also an element in the other. So one of the most powerful things mathematicians do is that they come up with ways of taking the objects that they study and then merging them together using operations to form new objects, right? It's like first we learn how to count numbers on our fingers. We understand what 3 means, right? We understand what 2 means. And then we come up with an operation like the operation of addition that can combine those together and to form a new thing, right? A new way of counting, right? We call that operation addition. And operations are, such a wide-ranging and flexible tool in math that most mathematical subjects that you study have some kind of operation associated with them, whether it's the operations of arithmetic on numbers, whether it's the operations of composition of functions, when you talk about functions and they compose together. That's a kind of operation that functions can do that numbers can't really do. When you study abstract algebra, Math 301, that really is fundamentally the study of operations. Or what kinds of operations can we define on a set of objects? And then what properties do those operations have? That is kind of describes what abstract algebra is. And so sets, too, come equipped with a variety of different operations we can do to take one set and another set and combine them together to form a third set. And there's a variety of ways to do that. And what's interesting about it is that they have a lot in common with the kinds of operations that we do on numbers. Right? We'll have an operation that feels an awful lot like addition. We'll have an operation that sort of behaves a lot like multiplication. When I say behaves like, it does things like distribute over parentheses, those kinds of things, which is a topic we won't quite get to in our course. But these operations, you can sort of hear echoes of other operations that we've studied elsewhere in mathematics and numbers when you start to get into the algebra that these operations define. But for sets, we're going to define 3 different kinds of operations. And the first of those operations, the union is the first one that we'll talk about. And the union of 2 sets, A and B, forms a third set whose elements consist of all of the elements from my original sets sort of all thrown into the same bucket. Right? So all the elements of A together with all the elements of B all get thrown into a single set. And that new set gets called the union, A union B. So we use a little U symbol to represent that operation. We can also write that definition using logic. using logical symbols, right? So the union of a set A and a set B is, and here's some set builder notation for it, it's the set of all elements of my universal set S, so whatever is a universal set for A and B, wherever all the original elements of A and B came from, which has the property that X is an element of A or X is an element of B. So the logical operation OR here is what's powering the definition of union. So I belong to the union of sets A and B exactly if I belong to A or I belong to B. I could also belong to both, right? The OR in logic is what's called an inclusive OR. So it's possible that I could belong to both sets A and B, and they'll also be in the union, right? But all I need in order to belong to the union is I need to belong to one of the sets that is being unioned together, right? So as soon as I belong to one of the sets A or B, I know that I must belong to the union because we're throwing all the elements into one big bucket, and that defines the union of two sets. The analog here is it's almost like an analog of addition. It almost seems like the union of two sets has as many elements as the number of elements of A added to the number of elements of B. That's not exactly true, but it feels true, and there are certain cases in which it actually is true. That you could explore those if you wanted to, and maybe that's a part of the exercises that we can do later. But anyway, that's the first and most fundamental operation for sets, is a union. We just pile all the elements from sets A and B together into a single set. Its alter ego, almost, is called the intersection. And the intersection of two sets is defined in almost the same way as the union, but it replaces the logical OR operation with a logical AND operation. So in order for me to belong to the intersection of two sets, I need to belong both to the set A and also to the set B, right? I need to have simultaneous membership in A and B in order to belong to the intersection of A with B. So we usually think of the intersection as just the places where the two sets overlap. It consists just of the elements that A and B have in common with one another, right? That is what the intersection of the two sets is. The set of elements from the universal set such that that element belongs to A and that same element also belongs to B. Right? So in the Venn diagram, so these are the diagrams that we frequently use to keep track of set operations. In the Venn diagram of the sets A and B, the intersection of A with B is just the place where the two ovals overlap one another in the middle. Right? That's the intersection. Whereas the union consisted of the entire MasterCard logo that's sitting here. The entirety of the blue, green, and yellow regions is the union of the sets A and B. But just the green union, the green region up here, is where we find the intersection of A with B. And so if the union was a logical OR and the intersection was a logical AND, then the third operation that we have to work with is our logical NOT. Right? And that's what we get when we talk about the complement of a set. The complement of a set consists of everything which does not belong to that set. Right? So I belong to the complement of A exactly if I do not belong to A. So it's a bit just like turning the whole universe on its head, inside out, right? Black is white, up is down, cats lying down with dogs. The complement of A is everything that A isn't. Right? And that presents a little bit of a logical difficulty because we can't define a set by saying what its elements are not. We also have to be able to say what its elements are, where they come from. And so that's where, again, set builder notation comes to the rescue. We say that the complement of A, which in this screen is written as A with a superscript C, but in the notation that you're using in your text, it's an over bar. So an over bar is sometimes used to indicate, and I think that's the notation that we're going to stick with because that's the one that your book uses. I'm just pulling from a different set of slides right here. But no matter how we denote it, it means it's the set of all elements from the universal set of A. And what that universal set is, sometimes it depends on context. So you often, your authors that you're reading or you when you're writing should always make sure that the context is clear. And if the context isn't clear, you should say explicitly, what is the universal set? Where are all these elements? Where do they actually live, given that they do not live in A? And we can maybe look at a couple of examples about why that universal set is important in specifying the complement. But those are the three big operations. Union, which sort of acts like an addition operation. It's the logical OR of two sets. The union of A and B consists of everything together in A and B, so all piled together into a single set. The intersection, which consists just of the overlaps between A and B. It's the logical AND, and from an algebra standpoint, it acts kind of like a multiplication acts. And then the complement, which kind of acts almost like a minus sign or something like that, like the opposite. It's all the elements that are not in A but which do still belong to the same universal set that A was understood to belong to. That forms the complement. So those are the three main operations that we want to work with. Let's do a quick example of sort of sussing out what are the elements of these, and then I'll give you an example to work on again in your breakout rooms. But let's look at this example together. So here we're given three sets that are called A1, A2, and A3. And we understand them by their rosters, so that's a mercy here. We don't have to decode any set builder notation. We understand exactly what the elements of A1 are, 1, 3, 5, 7, 9. A2 is 1, 2, 3, 4, 5. A3 is 2, 4, 6, 8, and 10. And then after that, we're asked to supply a roster for the sets which were obtained by these various set operations. So A1 union with A2, A1 intersection with A2, the union of A2 with A3, then intersected with A1. So now we're ratcheting things up. Our algebra is getting a little more complicated. The union of A1 with A3, then the intersection of A1 with A3, then unioned with A2. And then I think the third one I'll come up with a fifth one here, and we'll put a complement in it somewhere. But let's tackle the ones that are there first. So let me copy what we have over onto a whiteboard. So A1, 1, 3, 5, 7, and 9. A2, 1, 2, 3, 4, and 5. And A3 is 2, 4, 6, 8, 10. So I guess the first question that I want to ask before we go any further is, what do you think is a reasonable universal set that we could be using in this example? What universal set would be amenable to these three as subsets? It would be reasonable for us to decide based on the context that the universal set is the set of natural numbers, because in particular, all three of these sets are subsets of the natural numbers. Every element of A1 is also a natural number. Every element of A2 is a natural number. Every element of A3 is a natural number. But again, remember that this is a context-specific thing, right? It would be just as well, depending on what one's goal is in defining these sets, somebody might say that the universal set could be the integers, or it could be the rational numbers, or it could be the real numbers, or it could be the complex numbers. Or it could be a variety of different things, right? So I guess what I'm trying to underscore here is that there's not one answer to what is the universal set for a given subset or a collection of subsets, right? That really is dependent on what you're trying to do. And if the question about what the universal set is becomes a material question, and I'm going to try to make it one later on in this question here, then that's when that information is the most important for us to know. For now, I'm going to agree that let's just take the natural numbers to be a reasonable universal set. And so what I'll do is make a Venn diagram that conveys the information that we have in these three sets over here. And in my Venn diagram, I'm going to have a big rectangle around the outside, and this big rectangle around the outside is going to be my universal set. Call it S. And then for now, we're going to set it to be the natural numbers. Whoops. Okay. And so we kind of think of this square, this rectangle, as containing all the natural numbers. And my three sets, A1, A2, and A3, are then going to be subsets of that universal set. And I'm going to draw them so that they all overlap one another, like this. Try to color code them a little bit. So here's my set A1 in red, here's my set A2 in green, and here's my set A3 in blue. And so why Venn diagrams are so helpful is that it gives us the opportunity to write down all of the elements that are in these sets and write each one of them in only a single spot, in only a single region on this diagram. This is what gives Venn diagrams their power. So if I take A1, for example, it's got the numbers 1, 3, 5, 7, and 9 as its elements. So I could just start by writing all of those elements inside of the red circle and trying not to overlap them with any of the other circles. And then as I go forward, I say, well, what about A2? Well, A2 has elements 1, 2, 3, 4, and 5. But if I write them all over here, I've committed the only sin that we can commit in drawing a Venn diagram, and that's drawing the same element in more than one region, right? Namely, this number 1 right here now appears in two different spots. And we can't do that, right? Number 1 is only a single element of the universal set. And so it should only appear in one spot on this Venn diagram. Since it belongs to both the set A1 and the set A2, I should try to put it in a place where those two sets overlap in my Venn diagram. So instead of drawing the ones where I've drawn them, I'll put one here. And I've just recognized that 1 belongs to A1 and 1 belongs to A2. So what set operation does 1 belong to? What do we call that place where A1 and A2 overlap one another?
The intersection.
The intersection. Right. So that's just kind of warming us up for the work that we're going to do here. Notice that the same problem that we had with 1, we also have with 3 and we have with 5. Right? 3 and 5 I've written in 2 different spots on my Venn diagram, which is the only thing we cannot do with a Venn diagram. So I need to move 3 into that intersection, and I need to move 5 into that intersection. Okay. Now I have all of the elements of A1 and all the elements of A2 appearing in my Venn diagram, and each of them is appearing in only one spot. Right. So now let's work on A3. A3's got 2, 4, 6, 8, and 10. So I'll put them all into my blue circle. And then look again at my Venn diagram and realize that I have a problem. Right? I've got an element 4, which is appearing in 2 different spots. Right? It's appearing in A2, and it's also appearing in A3, so I need to fix that. I need to move it from A2 and A3 to the place where A2 and A3 overlap, the intersection of A2 with A3. Move 4 into that middle there. And we still have one more problem. We have 2 appearing here in A2, and it's appearing here in A3. And so that also needs to get moved into the intersection of A2 with A3. And now, taking a quick glance over this diagram, I think I have every element of A1, A2, and A3 is appearing somewhere in this diagram, and in particular, it's appearing in only one spot. So A1 is 1, 3, 5, 7, and 9. All of those are inside the red circle. A2 is 1, 2, 3, 4, and 5. All of those are inside the green circle. And A3 is 2, 4, 6, 8, 10. All of those are inside of my blue circle. Right. And each one appears once and only once. So we're in good shape. This is now a completed Venn diagram showing A1, A2, and A3 and their positions with respect to one another inside of my universal set. So now what we need to do is figure out how to determine rosters for these set operations and how the Venn diagram can help us to do that. So we have 4 that are assigned to us to do here. The union of A1 with A2, the intersection of A1 with A2, and then I have a couple that are more complicated. It's the union of A2 with A3 intersected with A1, and the intersection of A1 with A3, then union A2. And I'm going to add a 4th one. Let me add in here, how about this? Let's add in A1 intersect the complement of A2. So on my whiteboard here, I've written that as A1 intersection and then A2 with a line over it to mean the complement of A2. So that'll give us a chance to talk about all 3 of our set operations that we're tackling today. All right, so one at a time. Let's start with the union of A1 with A2. As we always do, we'll go back to the definition of what does union actually mean. And the union of 2 sets, A and B, consists of those elements in my universe which are either an element of A or are an element of B. So we're piling all the elements of the 2 sets together when we form a union. So for the union of A1 with A2, which part of this Venn diagram should I be shading in? So taking the union of 2 sets is like all the elements sort of getting in solidarity with one another. A1 union A2 is going to have as its elements everything taken together that belongs to A1 as well as everything that belongs to A2 as well as everything that belongs to both of them. Right, so all of the sets that I've shaded here in yellow are going to form the union of A1 with A2. And so if I want to write out a roster, I just have to list out all the elements that are in the regions that I just shaded. And if we like to list them in numerical order, which we are certainly not bound to do, we would count them off as 1, 2, 3, 4, 5, 7, and 9. So that would be a roster for the union. Right? So that's for the union. Now, what about the intersection? So that's the second question here. A1 intersection A2. Going back to the definition one more time. The intersection of two sets consists of those elements in the universe whose membership in A and whose membership in B are both true. So they have to belong simultaneously to A and to B. So where should I be shading on this diagram to find the intersection of A1 with A2? So the football shape where the red oval and the green oval intersect one another. The overlap between the set A1 and the set A2. That's the intersection of A1 with A2. And so a roster for that would be 1, 3, and 5. And we can always sort of check our work, right? For each of these elements, ask, is it true, for example, that 3 belongs to A1 and also belongs to A2? And we can go up here and say, well, 3 belongs to A1 because it's a part of its roster. 3 belongs to A2 because it's also part of its roster. And so because it belongs to both of those sets, by definition of intersection, it belongs to the intersection of A1 with A2. In these more complicated examples, we're guided at least a little bit by the old order of operations, which this seems like a funny place to meet the order of operations. But this is, again, sort of continuing the analogy of set operations with arithmetic operations. And what I mean here is that we have these parentheses that are being used in the notation to help us sort of guide our eye to what set operation is actually intended to be happening first. And until you learn rules of precedence for set operators, which really is just the order of operations for unions, intersections, and complements, we'll be using these parentheses to help guide us along the way, even when the order of precedence would otherwise make it systematic. So we won't care about order of precedence. We're just going to follow the parentheses right now. And so inside the parentheses, we're supposed to start with a union of A2 with A3. So the union of A2 with A3 is going to consist of all the elements of A2 together with all the elements of A3, so we'll shade both the A2 region and the A3 region to get ourselves started. And very often, I think it's a good practice to treat this like an algebra problem, where what we'll do is we'll just simplify what is A2 union A3 and just list out all those elements. 1, 2, 3, 4, 5, 6, 8, 10. So that's the union of A2 with A3. But then we're supposed to take that and intersect it with A1. So now the question is, where does the red circle intersect with the yellow shaded set? Right, so it's not the intersection of the red circle with one of the other circles. It's the intersection of the red circle, the overlap of the red circle with the yellow region. So which part of the yellow region is inside the red region?
1, 3, 5.
Just 1, 3, and 5. Exactly. If you're listing a roster for it, those would be the ones you list. If we're shading the regions that would be included in that set, we would shade just these 3. Right? So compare. This is what we had before. This was the intersection of A2 with A3. And this is where that intersection intersects with A1. And as you say, yes, a roster for that set would be the elements 1, 3, and 5. Whoops, not the greatest curly brace. I'm trying to fix that. If you become skilled at drawing curly braces, that's how you know you've been a mathematician long enough. I'm still not quite there, but I think these look okay. The next example is not that different. Inside the parentheses, though, this time we're starting with an intersection instead of starting with a union. So we're going to start by taking the intersection of A1 with A3. So we're going to be looking for the place where the red circle and the blue circle overlap one another. Whoops. And that is another football-shaped region here in the middle. What is a roster for that set? That roster has got nothing inside of it. So I'd be taking the union of the empty set with A2. Okay. So what is A2? A2 is the green oval here. And if I'm going to take the union of the green set with the yellow set, what am I going to be doing? I'm just going to be sort of shading all of those elements together, right? That's how we take a union by definition. And we belong to the union as soon as we belong to even one of the sets that's being unioned together. So all the elements of my yellow region and all the elements of my green region are going to be glued, sort of stuck together, thrown together into the same bushel. And so the elements that are going to belong to the intersection of A1 with A3, union A2, are going to be everything that's in one of these yellow shaded regions. So what is a roster for that? Just count all the elements that are there. 1, 2, 3, 4, and 5. By the way, it is a good thing that there is a union sign here, because what would have happened, what would have happened if I threw a intersection sign here instead?
Would be another empty set.
Yeah, exactly. So if we back up here, the intersection of A1 with A3 was this yellow empty set. What happens when we intersect the empty set with something? We're looking for the elements which belong both to the empty set and also to some other thing. But what elements belong to the empty set? None. Right? The proposition X belongs to the empty set is always a false proposition, right? So yeah, if I had had an intersection sign there instead of a union sign, we would have been done very quickly, right? Because we would have noticed in this intermediate step, as soon as we found a roster for that first empty set, we would have figured out, oh, well, this component is just empty, and the intersection of empty set with anything is going to end up being empty. So there are some cases, it's sort of like when you're doing arithmetic with the number 0, right? If I'm multiplying together a bunch of numbers, multiplying, intersecting, if I'm multiplying a bunch of numbers together and I find out that one of the numbers that I'm multiplying is 0, I can stop multiplying at that point because I know that my entire product is going to be 0. And the empty set behaves in that same way with respect to intersection, right? If I'm intersecting a bunch of sets together and one of those sets is the empty set, it completely kills off the whole intersection because nothing can ever belong to the empty set, and therefore nothing can ever belong to the intersection of the empty set with anything else. So that's what I'm continuing to kind of draw these parallels between the things we observe about set operations and the things that we've also observed about doing arithmetic like addition and multiplication with numbers. All right, let's do this last example that has a complement in it. And actually for this one, maybe I'll put my own set of parentheses around A2 complement just to kind of indicate that I want to start there. I want to start with A2 complement. So the first thing that we'll do is ask, where in my Venn diagram do I find the complement of A2? A2 is my green circle, so where is A2 complement?
Anything that's not in A2?
Anything that's not in A2. Returning to the definition, the complement of a set consists of everything in the universe which does not belong to the set in question. So for A2, the complement of A2 is going to consist of everything outside of my green circle. So I'm just going to kind of try to shade my entire universe, but not shade any of the green circle. So the part which is not shaded is exactly the set A2. All right, I hope that shading is reasonably accurate. And so here's where knowing what the universe is super important. If we were just stopping here and trying to come up with a roster for A2 complement, it looks like it would, well, we know for sure it would have the numbers 7, 9, 6, 8, and 10 in it. But it would also have a bunch of other numbers in it, like, oh, I don't know, 12. Right? 12 is not an element of one of my original sets, A1, A2, or A3, but it does belong to the universe that we selected, the universe of natural numbers, right? And so 12 would apparently belong to the complement of A2. But if we had picked a different universe, let's say that we picked the universe of integers, then not only would 12 belong to that, but also other numbers like negative 36 would also belong to the complement of A2, right? Where negative 36 wouldn't belong to the complement of A2 if the universe were the natural numbers, because negative 36 is not a natural number. So as soon as we start talking about complements, we have to know what the whole universe is, right? Otherwise, it's not going to be clear whether or not something does or does not belong to that complement. Does that make sense? So picking a different universe can actually give us different answers for what the complement of a set is. And mathematicians will sometimes do something like say, we're looking for the complement of the set A2 within, and then they'll say what the universe is. So the complement of A2 within the natural numbers will include 12, but it won't include negative 36. The complement of A2 within the integers will include 36. negative 36 rather. The complement of A2 within the real numbers would include pi, right? But the complement of A2 within the natural numbers or the integers would not. So knowing the universe is essential to being able to write down a roster for the complement of a set. We agreed at the outset that we were going to use the natural numbers for this universe, so that's what we'll do for now. And so there's a bunch of numbers that we know are going to belong to this complement, 6, 7, 8, 9, 10. But then there's also a bunch of other natural numbers that are part of the universe but which belong to neither A1 nor A2 nor A3, which would also belong to this complement. So I'm just going to kind of write ... there for now. Any questions about that question about complement and defining the universe before we move on? It turns out that question's not going to matter to solve this problem, because the next thing we're going to do is intersect with A1. And A1 is already a small enough set that we're going to be able to know for sure. And regardless of what the universe was that we selected, it's not going to matter to the answer to this problem. So it's just a more general issue. So to finish this example, we just have to know now, where does the yellow shaded region, which is everything in the universe except the elements of A2, right, where does the yellow shaded region overlap with A1?
7 and 9.
Just 7 and 9. Correct. So if I wanted to shade what this region actually looks like on my diagram, I'm going to be shading this portion, right? This two regions in my Venn diagram, right? It's going to consist of just 7 and 9 and nothing else. It's a bit like what we've done here is we've taken the elements of A1 and we've sort of taken away those elements which also belonged to A2, right? This actually has another name inside of set theory. It's called the set theoretic difference. So the difference, it's a bit like a subtraction operation for sets. The difference between two sets A and B, sometimes called A minus B using a regular minus sign. That's actually how your professor uses this notation. Again, this resource uses a weird backslash for that. But some mathematicians use one of those, some mathematicians use the other, and it's unfortunately approximately about equal numbers of mathematicians do each. So either way, but regardless of how it's notated, it means all of those elements which belong to A and simultaneously belong to the complement of B, right? So they belong to A, but they do not belong to B. That's what we mean by the set theoretic difference between A and B. So that's really what we've kind of constructed here, right? It's all those elements which belong to A1 and do not belong to A2. And that's how we end up with 7 and 9 here. So again, that set theoretic difference could have also written, again, different notation for this is A1 minus A2. Everything which is an element of A1 and is not an element of A2.